The next presentation is presented by Garcia Juan Manuel, and the topic is fracture toughness of similar titanium linear friction welds under monotonic and cyclic loading. Please.
Hello everybody, thank you Mr. Chairman. My name is Juan Manuel Garcia, and I will be presenting the part of my job during my PhD thesis. So the title for this presentation is the fracture mechanisms of similar Ti6242 Linear Friction Welds under monotonic and cyclic loading. I'm working at the Centre Matériaux d'Architecture in Paris under the supervision of Tino Morgan. And first, I would like to say a word. Yeah. Sorry. So we have two pieces, work pieces. One is fixed, and the other is describing an oscillatory motion. And after refraction of a second, we are going to apply enough pressure force in order to get the sound weld. Why is it interesting? Well, it's a very fast welding. We can perform dissimilar welds, and for optimized welding parameters, we can get an auto-cleaning process. So please notice the axis that I have chosen is the frame of reference. So we have F for the friction direction, P for the pressure direction, and T for the thickness. So some applications. So first here you can see that the mechanical fixations of the blades of the turbine disc have been replaced for linear friction welding. Just to be clear, this Garcia here is not me. We're a huge family all around the world, and we are all very passionate about fracture mechanics. So here in the second application, in order to get the wings in this structural beam, we're going to extrude the complex profile, and after a very extensive milling, we're going to get our workpiece. What do we propose? We propose to do a simpler beam and to add the wings by linear friction welding. As you can see, these beams are working, these applications are working under strong mechanical solicitation, loadings, so the mechanical properties need to be known. So this leads to the roadmap. So let us remember the title of this presentation, and we're going to study the microstructure, the monotonic behavior and tensile strength, the fatigue strength, and the fatigue crack propagations mechanism. We have worked with, we have chosen, two-phase titanium alloy with alpha grains situated in the vanadium matrix. So here's the microstructure. You have grains of 10 or 20 microns. So the first question, what is the effect of the weld? As you can see here, we have produced what we call the weld center zone. We have a very fine alpha prime entangled acicular microstructure, which shows an increased micro hardness. This increased micro hardness suggests a higher tensile strength. So if we were to do a tensile test, we should wonder where should the fracture take place. So here the tensile samples, paramaterial samples, and cross-welded samples. So we have a gauge length of 25 millimeters and cross-section of 18 square millimeters. So we have instrumented the tensor test with a standard monitoring, strain monitoring system. If you do not know this technique, don't worry, I will be very happy about giving you details about it at the end of the session. But for now, I would like you to know that we are going to get the 3D displacement field and the 2D strain field in the surface of the specimen that will allow the local behavior to be studied. So first, the tensor test results. So we have in colors the cross-welded specimens and in gray the paramaterial specimens. As you can see, the ultimate tensor strength is for both sets of specimens 960 megapascal. The ductility for the cross-welded specimens is reduced, and as you can see here, failure takes place far away from the weld. So we have the second conclusion of this presentation. Similar Ti6242 Linear Friction Welds exhibit a weld overmatch. So now we are going to study the local behavior. So here in the right we have a picture of the specimen with the blue rectangle which is going to show us the strain field on the surface of the specimen. We have the weld center zone here in the middle. And what we are going to do is, as we pull for every level of the macroscopic engineering strain, we are going to map in vertical lines the cumulative strain field in this generatrix line. So we are going to plot a so-called spatial temporal graph. This will allow us to study the strain history of this specimen, of this line, I'm sorry, in a 2D graph. So sorry. So what we see here, we're going to see with this, I'm sorry, this is a little bit slow. With the strain field, we confirm that the failure takes place far away from the weld, and we get to see the plastic deformation, which is very heterogeneous. So this information will show us the accumulated strain. But if we were interested in studying the instantaneous activity, we should take another variable. So which variable should we take? Well, of course, it is the strain rate. So here we have, once again, the special temporal graph for the strain rate. And please notice that I have normalized the strain rate by the maximum strain rate pi on every line. What does it mean? For example, let's do the exercise. Here, when the microscopic engineering strain is 0.05, the maximum strain rate is located at more or less 10 millimeters. Okay? So we confirm once again localization, well overmatch. But if you take a look somewhere here, when we quit the elastic domain, some activity is observed at 1.5 millimeters away from the weld. And this is very astonishing. This is very astonishing because, as we said before, we have a weld overmatch. Failure takes place far away from the weld. Nevertheless, the first steps of plastic activity take place in the surroundings of the weld. So the question about its origin may arise. Well, it is weld. Welds are known for having residual stresses. As you can see here in literature, we have found a certain agreement about the presence of residual stresses in the weld center zone. But a more interesting question could be asked is, now that we have established the localization of the first steps of plastic activity, we should wonder, where do the fatigue crack initiation sites take place during a fatigue test? So let's study that. So here we have the descending curve for the paramaterial in blue and the cross-welded specimen in yellow, with a strain ratio of 0.1 and a target life of 10 to the power 5 cycles. So as you can see here, for the target pattern life, the fatigue strength is slightly reduced. We're talking about the fatigue strength of 625 megapascals. But if we take a look to the cross-welded specimens, we can see that it's compromised with a very high fatigue life standard. For instance, these two specimens, the 1 and 5, were tested at the same stress level. But if you pay attention here, the life is very, very different. So we have a short life specimen and a long life specimen, the 1 and 5. So we're testing a cross-welded structure fatigue. And we would like to know where in this structure the fracture takes place. So here I'm showing 5 backscatter images of the surface of the specimen. I align them for, with respect to the weld center zone, and the red crosses are showing the fatigue crack initiation site. So for the specimens 9, 7, 5, and 3, failure takes place far away from the weld center zone. In particular, it's 1.5 millimeters more or less. And the one who has a short life takes place in the weld center zone. So we have 2 different localizations. So we'll study the fatigue crack mechanism for the first specimen, the one with the long life, the one who broke far away from the well. And what we can see, we can see fatigue bridges that converge to several points in the surface of the specimen. We can see it here also. And this could be explained by the fact that here we have said that we have residual stresses. So maybe the stress was enough to activate several crack initiation sites at the same location. And if we look closer, we can recognize here these features that convey the shape of the alpha grains. So we observe the stage 1 fatigue propagation. So now we're going to look the short life specimen, the one who had a very short life, and we can see that the fatigue ridges converge to a line in the center. Okay, so we have the fatigue crack initiation site over a line, and if you pay attention, you can see that the roughness of the fatigue ridges is smooth until this line, and then it becomes rougher. How can we explain this? We can imagine that given it is internal, the crack propagation happens in vacuum until it reaches the specimen surface. And there, the air can enter, and it's going to change the environment conditions. So now we have the propagation in air conditions. So we are going to take a look closer. As a reminder, we're talking about the specimen who broke at the weld center zone. Okay? So if you remember the morphology of the microstructure at this location, you should be surprised, because these features here does not look as like the microstructure that we were supposed to find here. These features convey the shape of the dendritic defect. It seems like locally the temperature during linear friction welding overreached the melting point, and so we have the dendritic defect. In the surroundings of these defects, we have facets that suggest a local brittle fracture. So we have a very flat surface on the surroundings of this dendritic defect. So we can imagine that we have an internal crack. So we have created an internal crack. And if you look at both sides of this internal crack, we can recognize here the shape of the microstructure, morphology of the microstructure. So we are in the presence of a crystallographic propagation. This is the stage 1-like fatigue crack propagation. So now we can imagine the fatigue crack propagation scenario. So this is going to be a schematic image. I have not measured the crack propagation rate. Yeah. So we have the brittle defect. We have a brittle fracture in its surroundings, We have the fatigue crack propagation over the mountain side. We have fatigue propagation stage 2 in vacuum until the air comes in, and finally we have a ductile final rupture. This is very interesting because we have several mechanisms in the same specimen. So to sum up, we have characterized the microstructure. We have found some defects like porosity, copper and zinc contamination. We have a well-overmatched fracture takes place in the paramaterial. We have an neoplastic activity in the wall center zone, which is probably attributed to residual stresses. And for fatigue, we have found a slight reduction of fatigue strength with a significant scatter. This induced defect was attributed to a contamination prior to welding that led to an internal fisheye crack reduced life. So I would like to thank you, Chairman, and thanks you for your attention.